Let's now do a sunspot analysis recap and look into some additional information about the topic. So to recap, one of the big takeaways here is that we were looking at an AR2 versus an AR9. And we also noticed from the spectral density that we seem to have a peak in the spectral density at 0 and also at 0.1-ish. And note that if we're trying to choose between an AR2 and an AR9, an AR2 cannot have two peaks, one at 0 and one at 0.1. It can have one peak between 0 and 0.5, which would be representative of a complex conjugate root, or it could have one peak at 0, or it could have one peak at 0.5, or it could have a peak at 0 and 0.5 if it was composed of two AR1s. But it can't have a peak at 0 and 0.1. That would require at least an AR3. So between an AR2 and an AR9, the AR9 would get the tip of the hat in that case. So that was a big takeaway of the initial part here of the sunspot analysis, but looking deeper into other analysis, the sunspot data is still being considered for analysis, to test new methods. And to sunspot data is really important. It's still being a topic of heavy research. And this is one in solar physics from 2021, forecasting of sunspot time series using a hybridization of ARIMA, ETS, and SVM methods. We've looked deeply into ARIMA and ETS, and SVM is support vector machine, which is also a popular data science model. And there'll be some information about that here. No shortage of information and tutorials on SVM. So let's just look at this article and see what the recent research is looking at. Throughout the article, SN will stand for sunspot number, but of course we'll have a little introduction here talking about how important sunspot data are. And here we have a breakdown of the ARIMA model that we're very familiar with, of the ETS model, exponential smoothing model we're very familiar with. And if you want to do some extra reading, right here in the article is the support vector machine information. Again, YouTube, lots of books. It's a very popular data science model that's being used here in this hybridization. So there's something called ensembling, where you could have two or more different models that each produce a forecast, and then we would take the average of those forecasts, or the median of those forecasts, or the max or min of those forecasts, and that would be a way to kind of combine all of the information from two or more different models together. This one is a hybridization, which is where they're producing one forecast from a variety of models. So actually a piece of this hybridization is an ensemble, but we'll see the breakdown of the method here, where in the end, different models play a different role in the forecasting process. So here is the proposed method that we're looking at here, and here is the diagnostic diagram. And that is, there's the time series, and it comes through and you get an ARIMA forecast, an ETS forecast, and an SVM forecast. Now this is the ensemble portion of the hybridization, where you're just gonna look at the three of these, and you're either gonna take the minimum, the maximum, the median, or the mean. They looked at all four of these different possibilities. And then from there, you get a forecast. And then it says here, take the time series and subtract the forecast from the time series. That's just the residual. And so then we're gonna do some modeling based on the residual, assuming that there's still some information about the series that's left in the residuals. That's kind of like the MA portion of an ARMA model, but we're doing it differently here, trying to model those residuals with an SVM. And then we combine those back together. So we'll take the forecast, add it back to the residual, and we'll get our final forecast. Very interesting, kind of straightforward method here that they feel that they found an advantage with. So let's see what they did. They're going to, first of all, here is for reproducibility and replicability, the algorithm. So defining the algorithm here, we're seeing that this is the SILSO data that we analyzed before. That is the sunspot, monthly sunspot data and yearly sunspot data. The monthly and yearly SN, again, sunspot numbers, time series from SILSO in CSV format, just like we did. So again, monthly and yearly, looking at these, that's a very familiar site for us. That's the monthly data, and this is the yearly data. So we know what we're dealing with. And of course, we're going to look at the forecast accuracy measures. One that we've looked at quite a bit is the RMSE. They're also looking at the MASE and the MAE. So awesome. let's keep scrolling down. Here's the simulation results and discussion. So here are the findings. Look at all the different models that they fit across the Sunspot data. It's important to note that they looked at one step ahead, a horizon of one, the next month or the next year, all the way across the time series. And for the monthly data, the RMSEs were in the 23s and 22s, where the lowest one was where they took the max. Remember, we said we ensembled those three different ARIMA, ETS, and SVM models. They took the max of the ARIMA, the ETS, the SVM, and then did their method where they used the SVM to model the residual and then added them back together. That gave them the lowest bolded here of 22.76. But you can see LSTM, a popular neural network-based model, was 23.3. ARIMA beat that. ETS beat those, at least in terms of RMSE. So what about the yearly data? Just kind of getting a look at the numbers. We have 29, 28, 44. LSTM is up to a 31. And then their method turned out to be the lowest here at 25.463. So again, there's a lot packed into this paper. All these are minus signs, meaning that the max, notice the max is missing. That's the one they're comparing. Every time there's a minus, it means that it beat this model. So it hands down beat it. This last model beat it in terms of RMSE, MAE, and MASE. So very interesting findings there. And that's just an example of some of the research that's still being done on the Sunspot data. And it can be used to evaluate new methods like this, or just trying to get a better forecast of Sunspot data, or both. And so we'll kind of leave it off there. Let's go back up to the RMSEs that we're looking at, and we can come on over to one that we've looked at, this stationary model. Notice that most of these are ARIMA is non-stationary, Trend ARIMA is non-stationary. These are all non-stationary because they have ARIMA in them. So, but we looked at an AR9. And so what we'll do here is just kind of take us back through that analysis. This is on the monthly data. So if I go ahead and plot it, very familiar picture, just like we saw on the paper and we've worked with before. If I do plots.sample.wge, I end up getting this slowly damping ACF with a couple of peaks possibly. At least we'll peak at 0 and a peak here at somewhere around probably 0.008. And again, just we've looked at that before, but this would be, we know that it's got about a 10-year period. There's about 12 months per year, so that'd be a period of around 120. 1 divided by 120 is 0.008, pretty consistent with that. So it looks like 2 peaks there. Again, would require more than an AR2. Our other candidate model here, as we'll see, is an AR9. We'll let AIC5 go from 0 to 10. And yeah, so it looks like on this one it picked a 10. I went ahead and went with a 9 just to stay consistent. Again, there's nothing, it just has the lowest AIC. That one does have the lowest AIC, but it's in the top 5. A reasonable model here would be an AR9. Again, encourage you to check them all out. But here I'm estimating the 9 fees, fee 1 hat, fee 2 hat, all the way to fee 9 hat. And so we've got that. And then I'm going to do a rolling window ASE or RMSE on the Sunspot data. We're going to look at a horizon of 2 here. This actual function won't do horizons of 1. So it's actually handicapping this just a little bit. Should do better with a horizon of 1 than it does looking 1 and 2 out. But just as kind of a baseline here, we'll run that. It's when 3,253 windows. It got a rolling window RMSE of about 21.116. And again, we have the histogram of the ones that we saw, so on and so forth. So let's remember that one. In fact, let's compare it right now. So on the monthly data, a 21.116 beats all of these. Again, and it should be even better than that because with a horizon of 1, right, it should do better at forecasting 1 in the future than it does 1 and 2 in the future. But regardless, just as kind of a quick baseline to compare, we could write more code and do more analysis if we really wanted to write maybe a paper to extend this paper or in response to this paper. But let's go ahead and look at the annual data. And so I'll go ahead and plot the annual data. Let's go ahead and dev.off and then plot the annual data, which should look fairly familiar. It's the same data, but kind of smooth to be yearly instead of monthly. I'll go ahead and plots.sample.wge so we can check it out. It'll look pretty similar to us. And Sunspot dot 2.0. Sunspot. Little typo there. Always good. There we go. So very quick. There's our two prominent peaks. One over, right, this is the yearly data, so that's about 1 over 0.1 or a little bit less, showing the period of 10 or 11, and another one at 0 showing these kind of wandering amplitudes here. So again, AR2 just doesn't have the capacity to model that. It can only model one frequency between 0 and 0.5, and that would be it. Or it could have one at 0 and 0.5. It can't have one at 0 and somewhere between 0 and 0.5, like this one does. So we're going to do the AIC5, but looking at that AIC5, we'll have an AR9 is the picked one, I've always seen before, but just confirming it. And noting, let's go ahead and estimate those 9 fees. So I'll go ahead and do that. And finally, let's do the rolling window AIC again. This is on the Sunspot data with a horizon of 2 and then the fees. Again, we're just doing a horizon of 2 because this function currently won't have a horizon, won't do a horizon of 1. So again, this should be a little bit lower than what it be as we see at horizon of 2. So this one is 23.445. Interestingly, that's averaged over the entire series, just like they did in this paper, and for hands down beats even their model here. All of these are pretty much non-stationary models. I guess the ETS isn't, but the ETS didn't perform too well anyhow. The pretty interesting. Definitely worth some extra look here. Is that sometimes a stationary model, sometimes just guessing kind of in the middle over time. The farther out we forecast, we kind of tend towards the mean. Again, only here we're only going a horizon of 2, but very interesting that it's returning kind of hands down significantly better RMSEs than was found in this paper. So just a look at what you can do with time series, what you can do with the current research, how you can participate in the current research, and just really just have a lot of fun with it, given what you now know about REMA models, ETS models, learn about the sport vector machine models, learn about LSTM models, bidirectional LSTM models, and get out there and really participate and contribute to the current literature. It is a blast, and that concludes our Sunspot recap with a lot of additional info.